Hello physics students. So in the last few videos we've been talking about waves, but always about one wave at a time. In this video what we're going to be learning, or what you're going to be learning, is what happens when there's more than one wave at a particular location in space at the same time. And so what happens is called interference. And to help us understand the details of what goes on when two waves meet in one place, we're going to use this principle called the principle of superposition. So I have two waves here, and you could see maybe there's one person at this end of the slinky shaking their hand up like this, up and down, and then someone at this end. And they have unequal amplitudes, and they are moving toward each other like this. At some point, they're going to find themselves at the same place at the same time. What will happen is that the slinky will displace with a combination of the two displacements. For example, if this is 2 meters and this is 1 meter, then the net displacement would be 2 plus 1, or 3 meters high. It produced one big wave, the height of the two heights combined. But an important point is that the widths do not add. When they perfectly overlap, if this is 1 meter wide and this is 1 meter wide, you don't get a wave that's 3 meters tall and 2 meters wide. It's still only 1 meter wide. It's just that one wave is on top of the other, so it'd make one big giant wave 3 meters tall, same width. So that's the principle of superposition. What we're going to do now is see some old computer animations of different kinds of waves coming together and doing this thing, interfering with the principle of superposition. So give me a moment to reconfigure the camera. So I was going to show you some old film footage of some waves interacting, computer animations to show the principle of superposition. But I found this website that does a much better job because it's interactive. So here's the web address. In fact, what I'm going to do is I'm going to put a link to this site in the Google stream. And so you could go and visit this to play around with different kinds of waves interacting, so you could really learn the principle. Or you could even use it on tonight's homework, which involves you drawing the net effect of two waves interacting. So if you want, you're not sure, you can actually visit this site and just simulate the waves and watch and just record the answers to the night's homework. So this is what loaded when I loaded the site. But what I'm going to do is I'm going to change this into like the first half of a sine wave, or at least as best as I can. Now notice that this sort of, it's more angular, but it kind of simulates a sine, the first half of the sine function. And I'm going to do the same thing over here. So I'm making two half sine pulses. And what we're going to do is when I hit animate, you're going to see these waves come and meet in the middle. And down here shows the sum, the net effect of, if this were like a rope or a slinky, what would happen when the waves meet. So let's watch. Okay, so you see they're almost completely overlapping, and you see now the two waves here are on top of each other, so it looks like there's one wave here, but there are actually two that are interacting down here. As I said, we could use the principle of superposition to find the net effect. The two waves are both 0 here, so right here 0 plus 0 is 0. But over here, one wave is 2 high, 2 boxes high, and the other wave is 2 boxes high. So the net effect at this point is 4 boxes high, the net displacement. In the middle, we have 3 and 3, so the net displacement at this x-coordinate is 3 plus 3, or 6 units high, and here 2 and 2 again, which gives us 4 boxes high, and here 0 and 0 again, gives us 0. So the net effect is like a sine, or a half of a sine pulse, that instead of being 3 high is now 6 high. But notice the width did not change. We still have 4 boxes wide here and 4 boxes wide here. So again, the heights add only, not the widths. And then we continue on, and you see the waves pass through each other. Now they do indeed pass through each other. Let me rewind here. And if you just watch here, what a lot of students might think is that these waves bounce off each other. Watch what happens. I animate and look, it looks like they come in and boom, they bounce off and head the opposite way. That's not what really happens. What happens is the waves pass through each other. The one that was blue here ends up on the right. This is more effectively seen if I turn this into a negative sign pulse. So here, we'll watch these come together, and to help your memory, what I'll do is I'll put this little piece of paper here to remind you that on the left side, well, maybe I'll raise it up a little bit. Oh no, actually, yeah, let's leave it down here. That the positive wave started on the left and the negative on the right. So let's watch them, and then as they meet, I paused it. So what happens is we have 0 and 0 make 0 right here. And then we have positive 2 and negative 2 add to 0. Positive 3, negative 3 add to 0. Positive 2, negative 2 add to 0. And 0 and 0 add to 0. So if you were to really snap a picture, if this were a spring and at this moment you snapped a picture, you would see the spring completely flat. You might conclude that there are actually no waves there. There are two waves, a positive and negative one that at that moment added to 0. And then as time went on, they would continue through. And here you see that what the positive wave used to be on the left, and now it ends up on the right. They did pass through each other. I'll play this again without any pauses so you could watch this positive wave end up over here as it passes through. And there it is. So, and basically this is also supported by your everyday experience. Sound, as you know, we already talked about, is a wave also. Imagine a person standing over here and another person standing here, and they talk at the same time. The voice of one person, the sound waves are heading this way, the sound waves of this person are going that way. They do not bounce off. If this is person A, person B can hear person A because the sound waves of the voice pass through the wave and continue on to the ear of the observer over here. And same with this observer being able to hear that one. If the sound waves truly bounced off, if two people talked, they would not hear each other. The sound waves would just bounce off and you would just hear yourself. So clearly waves do pass through each other. They only interact in the middle. So let's continue on with some other examples. Now, the principle is shown very nicely with a square wave. So let me create a square wave here. Now, if this were a spring, oops, I was going to do this square wave over here. So let me fix this. If this were a spring, it would not be possible to make a square wave like this. You'd have to yank your hand up instantly like this, wait a second or two, and then yank your hand down instantly. Basically, the spring would snap. But these kinds of waves are possible with electricity and wires. You could make the voltage pop up nearly instantaneously, let that pass through the wire for some time, and then drop it down to 0 nearly instantaneously. So the first thing that I'm going to do is I'm going to add that to that another, not a square wave, but a rectangular wave. So what we're starting with on this side is this rectangular wave. So I'll put that there for our reference and for our memory. So I'll let this go through and then I'll pause it right there. Now, what's happening is we're adding these two waves at this moment. Notice that this wave here is 4. And the 4 right here, and the other wave is 0 because, you know, it hasn't reached here yet. So 4 plus 0 is 4. In fact, we're adding 4 plus 0 as we keep going along until we get to this point. So 4 plus 0 is 4 all the way till here. And then what happens right here is we've got 4, positive 4, and positive 1. That adds to positive 5. 1, 2, 3, 4, 5. And the same with this x-coordinate right here. We're adding 1 and 4, which gives us a total of 5. And then once we get to this x-coordinate, we're adding 1 and 0. So 1, 1 and 0, 1, 1 and 0, 1. And then we're adding 0 and 0 here. So you see at that moment, that's how those waves add. Let's continue on just a little bit more. Oh, right there, perfect. So what we have here is when the two waves perfectly overlap, we have one that's 4 tall and the other one is 1 tall, which adds to 5 boxes tall. So 4 and 1 make 5 height. But notice the width of both of them was 4, so the width of the total is still 4. The widths do not add to 8, only the heights add. And then we continue onward. And again, the waves pass through each other. So the tall rectangle was over here, and this time I won't pause. They don't bounce off each other. The tall rectangle passes through and ends up on the right side when it started on the left. So let's take a look at another example. Let's do 4 and -1. Okay. So now what we're going to do is we're going to add these together. I'll stop when they overlap right there. So what we have is we've got +4 and -1 added together gives us a height of only +3. +4 plus -1, +3. And that's the same all throughout. So the wave is only 3 high, but the width didn't change. The width is still 4. And so we continue on. And there we are. Once again, the tall rectangle began on the left. It did not bounce off. It passes right through the other wave. And same with this one. They pass through each other. All right, let's do another example. Let's keep this tall rectangle. And then what we're going to do is we're going to make a little nub of a triangle like this. So now let's animate. Let this go. And there we are. So what we have is 4 plus 0, 4. 4 plus 0, 4. 4, +4 plus -1 gives us only +3 in the middle. And then here we've got +4 and 0 again, which is 4. +4 and 0 again, which is 4. So we add onto the rectangle a tiny little triangle, a little divot in the top. That's the sum, the net effect. And we continue onward. So again, we'll see that this rectangle, or square I should say, will pass right through the triangle, and the triangle will pass right through the square. Rectangle ends up on this side. Okay? All right, let's do maybe one more. Let's do a rectangle and a downward sine graph. So what would this add now? Well, let's take a look. So again, we could just use the principle of superposition. We've got 4 over here and 0 for the other one. 4 plus 0 is 4. At this x-coordinate, we've got +4 and -2, which add to +2 right here. And then at this x-coordinate, we've got +4 and -3, which add to +1. +4, -2, add to +2. And over here, +4 plus 0 gives us +4. So that's the sum of those two waves, a square plus a downward sine graph. And again, they pass through each other. We could see that by rewinding. The rectangle started on the left, and we will watch that it doesn't bounce off. It passes right through. Okay? So that's the principle of superposition. Nicely shown on this website. Again, the link should be there, and you could use it to do your homework. What you're drawing in each homework example is, I give you this, for example, possibly, and then what you're drawing is what happens when they perfectly overlap. The net effect of the two waves added together at the exact instant where they perfectly overlap in the x-coordinate system. So, all right, so that's it for the animations. Let's go back to our notes and see what we could jot down to summarize. So now I'm going to do a couple examples summarizing what we saw in those animations. In this example, we have a square wave. As I said, this would only be possible in an electrical wire with a voltage that can jump up nearly instantaneously and drop down. But let's suppose we could do this with a spring. We could pull our hand up very rapidly and drop it very rapidly, make a square wave that's both 3 meters high and 3 meters wide, and it's going to travel down the spring this way. And at this end, at the same time I created that wave, someone does that same motion but creating a 1 meter tall and a 1 meter wide wave. When these two waves eventually meet in the middle, we add up the displacements for all points from one end here to the other, and we see that this is going to be 3 meters high right here. But then on top of it is this 1 meter by 1 meter box, a wave. And so that's what the spring would look like if we could snap a picture at that exact instant. Then what happens is the waves pass through each other, and they do not distort each other in the end. We have the same exact wave passing through over here, same exact wave passing through over here. So that is true of waves when they meet and interact or interfere. In the end, they don't change each other permanently. And this is, it makes sense from a common sense standpoint. Think about this. You've got two people here, and they start talking at the same time. And what happens is in the middle, the person in the middle hears all the voices kind of jumbled up. That's the superposition. But then what happens is the voices don't bounce off each other. That's what a lot of students think. They think the waves bounce off, as we saw in the animation. That's not true. What happens is this wave of this person's speaking passes through the other one, and then they can hear each other because their sound waves pass through each other without permanently distorting. So that's a key principle. So let me create a pause, allow you a moment to copy these notes down. Second example. So now what we do is, maybe I'm at this end and I yank my hand up, yank it down and make a 3 meter by 3 meter box wave, and someone over here pulls their hand down and then up and creates a 1 meter by 1 meter box wave in the downward direction. That's why I have a negative for the displacement. These waves approach each other. When they meet, the heights add. So in the middle, this is only 2 meters tall, but on the edge here, it's 3 meters tall because the downward 1 meter displacement doesn't act on the ends. So maybe we should add that right here, that this is 2 meters tall in that well. And then once again, this wave passes through with no permanent distortion. This wave passes through no permanent distortion. So let me create a pause to give you a moment to copy these notes down. All right, so now I'm gonna talk about two more ideas, something called constructive and destructive interference. This is a common thing that shows up on the Regents. So what I'm gonna do is just write it down and I'll explain. So here's constructive interference. What happens is wave A comes and wave B comes this way. Notice they're both crests. So when two crests meet and make one wave that's larger displacement than either of the two original waves, then that's what we call constructive interference. And notice this is taller but not wider. And then after, as I already mentioned, the waves pass through each other, so B is now over here, A is now over here, and they continue on undisturbed or undistorted. All right, so let me create a pause to give you a moment to copy these notes down. Next term, destructive interference. Okay, that's destructive interference, but I just want to mention one more thing about constructive interference. I said that constructive interference occurs when a crest and a crest meet together and they produce a bigger wave. It also happens when a trough and a trough meet and produce one larger trough. So maybe like -1 meter, and then they combine to -2 meters, but the same width. That would be also constructive interference. Now destructive interference. So instead of crest-crest heading toward each other or trough-trough heading toward each other, we've got a crest and a trough heading toward each other. Let's see. When they meet and perfectly overlap, if you were to snap a picture of this spring or rope or slinky, whatever it is, at that moment, you'd snap pictures, say, oh, look at that picture, there's no waves there. There are actually two waves there. It's just that at that moment, they're adding to zero, okay? But they don't destroy. The name is a little misleading. It says, you know, when you think something is destroyed, it's gone, it's broken, it's never coming back. Not true with destructive interference. They only sort of destroy each other at the instant they overlap. But the waves pass through just like over here. So the trough reemerges and the crest reemerges. And so that's destructive interference. Now, let me create a pause to give you a moment to copy these notes down. There's one more thing that I want to talk about, noise-canceling headphones. Okay, so noise-canceling headphones do not work like typical hearing protection that are just try and muffle the sound, try and block it. So I have like earmuffs that I wear when I cut the grass, mow the lawn so the mower doesn't damage my ears, or when I'm cutting with a saw to protect the ears. And that's just a simple sort of, as I said, blocking the sound. What noise-canceling headphones do is something even more sophisticated, even better than trying to block the sound. What they do is they have a little microphone that listens to the sound that's on the way in to your ear. So maybe, you know, you want to listen to some nice music, but, you know, people are in the room and they're talking and you'd like to hear just the music, not them talking. So what the earphones do is they hear the people talking, that sound heading into your ear, and then they rebroadcast that exact same sound. And you might say, why would they do that? The headphones, it would make the sound louder. People talking and then the headphones add more sound. Shouldn't it get louder? If the crests and crests matched, but the headphones do it a step behind. So as a crest, well, actually sound is a longitudinal wave, so I'd have to draw compressions and rarefactions, but that would be more or less clear, I should say, than this. I'm drawing sound as a transverse wave, which is not correct, but it shows the principle of how these headphones work better. So that's why, just note that. So let's suppose sound is a transverse wave. It's going into your ear. The headphones rebroadcast the sound of the people, but a step behind, so that basically it's creating this exact sound. So this is the headphones. And what happens is every time the people talking, their vocal cords are making a compression going into your ear, the headphones are sending a rarefaction into your ear of that same sound. And then when the people talking are sending a rarefaction into your ear, the headphones are creating at that exact instant a compression to go into your ear. And the net result is zero amplitude. The sound destructively adds to the original sound, and what goes into the ear is silence. Okay? Now, they don't work perfectly. You put them in and you could still hear things, and that's because sound goes more than one path into your eardrum, not just into your ear canal. It can also strike your body and go through your body. So there are other paths the sound can take through your body, and so it doesn't perfectly cancel those, but anything going into the ear is pretty close to canceling those sounds out. So that is interference we learned about. Just go back in your notes, review the principle of superposition, that the Y's add, not the widths of the waves. Make sure you understand that. And then go back, look at the examples of how you can add these oddly shaped waves. You know, they don't, as I said, they don't really happen in real life. They happen on physics tests because when you have odd shapes, it's nice and easy to see the principle rather than just having smooth curves like this. So look at those two examples I did. The homework questions will be very similar. You're drawing the shape of what happens right when they overlap. For each interaction, you should be drawing a separate diagram of the point when the waves add, or I should say interfere. So look those over, and then also know these terms, constructive and destructive interference, and know that the waves don't really destroy, they pass through, but at that moment they add to zero. So that's it for today. I hope you enjoyed the video. I hope you enjoyed the computer animations. I'll see you in the next physics video.